Next speaker. Our next speaker is Dr. Umesh Chandra from Garhwal University, India. And I see that there is a title change. So the title of his talk is Some Fixed Point Theorem on Finite Product of Metric Spaces. And Dr. Umesh, you can start your talk.
Okay. Now may I start?
Yes, sure.
Okay. Thank you. So the title of my talk is Some Fixed Point Theorem on Finite Product of Metric Spaces. So you have heard a lot of historical development of fixed point theory for the last so many lectures. So I will not go in the details for that, but here especially with a view to generalize the Banach contraction principle, Matvosky proved a fixed point theorem for the system of n maps on the finite product of metric spaces, which is known as Matvosky contraction principle. Matvosky fixed point theorem is applicable to find the solution of system of functional equations, which attracts several mathematicians to work along these directions. So in this talk, we will discuss some extensions and development of uh, Matvosky contraction principle and some recent results. So fixed point theory, you know that existing area of the research in the field of nonlinear analysis. This theory has been revealed as one of the very powerful and important tool in the nonlinear analysis and has tremendous applications in various branches of mathematics and mathematical sciences. The concept of fixed point plays a key role in fixed point theory, and the theorems concerning the existence and properties of fixed points are known as fixed point theorems. So, just you can see some definitions like the fixed points. This definition is discussed so many times that if you have a point belong to the set, then this fx and there is a function f. So then the fx is equal to x. So then the x is called the fixed points. You can see there are examples of the fixed point, that how we can find the fixed point, the unique fixed point, two fixed point, many fixed points, and no fixed points. So these are the examples for this. So, on the historical point of view, that initially Brouwer fixed point theorem was one of the early achievement in the nonlinear analysis due to the Dutch mathematician L. E. J. Brouwer in 1912. Brouwer fixed point theorem asserts that a continuous map on a closed unit ball in Rn has a fixed point. And the Banach fixed point theorem is probably most remarkable and well-known result in the field of fixed point theory, and named after the Polish mathematician Stephen Banach. On the other hand, the study of fixed point theorem on multivalued maps was initiated by Kakutani by generalizing the Brouwer fixed point theorem. However, the development of geometric fixed point theory for multivalued maps was initiated by Nadler, and the Markin and Nadler introduced the concept of multivalued contractions using the notion of Hausdorff distance and established the fixed point result for multivalued maps. In the last several decades, a number of generalizations of Banach contraction principle have been obtained by several mathematicians. Among various generalizations of the Banach contraction principle, some important generalizations are discussed here. So in 1969, this Meir-Giller gave an important generalization of the classical Banach contraction principle and obtained a remarkable result in the complete metric space. The result of Meir-Giller is given as follows. Just you can see that there is a complete metric space and the map is defined, and there are some conditions given in this 2.1. So then the f has a unique fixed point in y. So another extension is this is named as the Jung contraction principle, so that he extends the Banach contraction for the two maps. But in between this, the K. Gobel gave a result for the two maps, but he's unable to find the fixed point, only constant points. So here, by using the condition of commuting map, so then he finds the fixed point for that, two common fixed point for these two maps. So another important generalization of Banach contraction principle was obtained by Matvosky in 1973. Generalized the Banach contraction principle for a system of n maps on a finite product of metric spaces and proved a fixed point theorem for such system of maps. So we accept the following notations of Matvosky and Zervik and myself and Jangwan. So these are the notation for this, that the AIK n cross n square matrix with the non-negative numbers. This IK vary from 1 to n, and these are defined like this. The CIK, this matrix is recursively defined by like this. So then the following lemma, after that Metkoski gave a lemma on this, that if the CIK which are defined in this the previous notations, so then the system of inequalities, this summation AIK RK is less than RI, that the I vary from 1 to n, has a positive solution R1 R2 Rn if and only if the following inequalities hold. So this paper, this result is announced in the Polish Academy of Sciences in 1973. So, and this is published in his dissertation. So let this xi be from I vary from 1 to n be complete metric spaces, and this ti from x1 cross x2 to xn from xi means this map is from the product space to a single space. If there exist non-negative numbers aik, ik is 1 to n, such that this 3.1, these are defined in the previous conditions, the 3.1, 3.2, and 3.4. So then this di, ti, x1, xn, this ti, y1 to yn, this is less than equal to this summation k is equal to 1 to n, aik, dk, xk, yk, for every xk, yk belong to this xk, and ik is equal to 1 to n. Then the system of equations xi is equal to ti, x1 to xn, I is equal to 1 to n, has exactly one solution. X is equal to the x1 to xn, such that this xi belong to xi, I vary from 1 to n for any arbitrary fixed point. So the sequence of successive approximations, this xi m plus 1 is, these are the notation for this, that we are defining the sequence like this. So these above the results usually known as Metkoski contraction principle, and called Metkoski this by Reddy and Subramaniam and Singh Garula. Zervik extended the result of Metkoski and gave a generalization of adolescent fixed point theorem for a system of maps on the finite product of spaces. Following the Metkoski contraction principle, Reddy Subramaniam generalized the Metkoski fixed point theorem and Krasnozelski fixed point theorem, respectively, for the sum of two transformations. So after seeing Krusista, combined the idea of Metkoski and Zervik and proved a common fixed point theorem for this. Means they extend this result for the two system of maps and find the solution for the this SIX is equal to XI is equal to TIX, has a unique solution x1, x2, xn, such that this XI belong to XI, I vary from 1 to n. So further Singh and myself extend the result of Metkoski for three system of maps, and by extending generalizing this contraction theorem, and here you can read the conditions that pi, qi, ti, these are the three system of maps, and just we are taking this contraction condition, and then we have we find that the coincidence solutions for this, that the pix is equal to tix is equal to qix is equal to this xi. So such that this xi belong to xi and I vary from 1 to n. So now initially what happened that in 1991 Singh Garula combined the idea of Jung and Metkoski. So after this time we are unable to find that how to find the fixed point for this. And then we define the coordinate wise commuting maps, and we extend the result of this Jung for this product of metric spaces by defining. So this coordinate wise commuting at a point x. So if you are taking this pi, this t1x, this tnx, and ti p1x, pnx for all I is equal to 1 to n. So this is simply, you can say that these two system of maps are coordinate wise commuting on x if and only they are coordinate wise commuting at every point of x. So these are the examples we have given, the examples that the coordinate wise commuting maps. So you can see these examples. And the coordinate wise, then we define the coordinate wise weakly commuting maps. So this coordinate wise weakly commuting, you know that for the single for the simple metric space, this is defined by the SSA, and then we have defined for these coordinate-wise weakly commuting for the product of metric spaces. And now you can see that evidently the coordinate-wise commuting system of maps are coordinate-wise weakly commuting. However, the weakly commuting system of maps need not be commuting. You can see the paper. And this is the examples supported for that weakly commuting, but not coordinate-wise commuting at x is equal to 0, 0. This is the example given by us. Then we have extended this result for the four system of maps by taking this type of conditions, that we are taking just not the completeness of whole space, that just you are taking this SIX intersection TIX is complete subspace of XI. So then for these four system of maps, we have a unique common solution by taking this type of this contraction condition and defining a other constant, this b, that this 0 is less than equal to b is less than equal to 1 minus h, where this h is defined like this. So then further, we have also taken this as the result for this new type of contraction condition. We extended this result for by taking one more constant there, and we have also find the result for this. So later on in 1995, we generalized the Minkowski contraction on the product of complete metric space by introducing coordinate-wise asymptotic commuting mappings, and this definition is like this. So this asymptotically commuting, we have given the definition and also the examples for this, and also prove some theorem for this. When we are taking the asymptotic commuting mappings, you know that this is more, this is the weaker form of the commuting map. And then we can find the solution for this. Pix is equal to Qix is equal to Xi, Six is equal to Tix, has a unique common solution x1 to xn, such that this Xi belong to Xi, I vary from 1 to n. Again, we have taken this coordinate-wise R commuting mapping, that you know that the Professor R.P. Pant also defined the R weakly commuting map, which is independently the compatible map and this R weakly commuting map, these are the independent. So on so we can define this, we can we have given this definition for that, and we have also given some examples for that, for justifying our definitions. So this notice that the coordinate-wise weakly commuting maps are coordinate-wise R weakly commuting. However, the coordinate-wise R weakly commuting maps need not be coordinate-wise weakly commuting. The following example illustrate this concept. So since each x belong to x1 cross x2, so this is the detail of this example. So I think there's no need to explain this because the shortage of time. So now this is the for the linear system of math. A system of math P1 to Pn is said to be linear if this P1x is this Pix plus Pix. So we have also proved some theorem for this Banach, when we are taking the product of Banach spaces, and then we are taking the product of the C is the closed convex subset of X with a condition that this Ci is subset of Xi, I is equal to 1 to n, C is equal to C1 plus C to n, I is equal to 1 to n. So then we have the result to by myself and Jangman for two system of maps on the finite product of Banach spaces are given as follows. So when we are taking this C as the closed convex subset of this Banach space, and we are taking the two system of maps, so then finally we have got then the system of equations Six is equal to Tix is equal to Xi has a unique common solution such that this Xi belong to X. So the study of contractive maps which does not force the map to be continuous at the fixed point was initiated by Pant. This 30 in 27, Pant introduced a notion of reciprocal continuity and proved a common fixed point theorem for the four maps without requirement of the continuity of any maps. So Pant defined that two cell map S and T of a metric space YD are called reciprocally continuous if limit stxn is equal to st and limit stxn is equal to tt. Whenever xn be a sequence in y such that limit sxn is equal to limit txn is equal to t for some t in y. So later on, this Panthata generalized the notion of reciprocally continuous to the weak reciprocal continuity, and which state that the two self-map S and T of a metric space YD are called weakly reciprocally continuous if limit STXN is equal to ST and limit TSXN is equal to TT. Whenever XN is a sequence in Y such that the limit SSN is equal to limit TXN is equal to T for some T in Y. Motivated by the work of Singarola and Pant 27 and Pant et al., we extend and generalize the Minkowski contraction principle for the non-continuous map. We do this by introducing some new class of maps coordinate-wise reciprocally continuous and weakly reciprocally continuous system of maps. So these are the definition for this, that the two system of maps T1 P2Pn and T1 Tn are said to be coordinate-wise reciprocally continuous if and only if limit this and this piz and this limit ti p1 to pn is tiz. Whenever there exists a sequence xm in x such that this pix and this limit tixm is equal to zi. So if each member of the system of maps is continuous, then the system of maps are coordinate-wise reciprocally continuous, but the converse need not be true. The following example will illustrate that this result. So you can see this example is given by us that the system is, these are the reciprocally continuous but not continuous. So here we have a detailed discussion on this example. Now we state our result on reciprocally continuous map. So by using this reciprocally continuous map, we have proved this theorem that when we are taking the fourth system of maps and then using that contraction condition, but taking that the system, these maps are the coordinate wise reciprocally continuous, means the maps need not be continuous. So then we can get the unique solution for this pix is equal to qix is equal to xi and six is equal to tix as a unique common solution. So also we have defined this coordinate-wise weakly reciprocally continuous map like this reciprocally continuous map for this, and we have also find some result. We have also given the example in support of our result, and now this is the detail. So just we can remark here and notice that the above definitions with n is equal to 1 are standard ones for the commuting, weakly commuting, and asymptotically commuting, also called compatible are weakly commuting maps, reciprocal continuous maps, and see also that the weak reciprocal continuous maps, asymptotically commuting or compatible class of maps includes commuting and weakly commuting maps. Commuting maps are necessarily weakly and asymptotically commuting both. The commutativity, weak commutativity, and asymptotic commutativity are equivalent at the point of coincidence of two system of maps. So next we prove some common fixed point theorems for three system of maps using the concept of coordinate-wise weak reciprocal continuity. So these results are stated like this here. Similar to the previous conditions, only change is here that we are taking the weak reciprocal continuous. So this is some other result for this. And now we notice that the several corollaries may be derived from the above theorems by selecting the system of maps suitable for example taking SIX1, this one is equal to I is equal to 1 to n in the proof of theorem 3.9 or putting this one. So in the proof of theorem 3.10, we obtained a solution for two system of maps. So just these are the remarks that the Young contraction condition, this may be obtained from this 3.13 when this b is equal to 0 and si x1 to the t x7 when this n is equal to 1, and similarly for this b is equal to 0, p I x1 to xn is equal to qi x1 to xn, n is equal to 1. Minkowski fixed point theorem is obtained as a corollary from this theorem 3.9 when this b is equal to 0 and si x1 to xn and ti x1 to xn is equal to xi for each xi belong to xi. And similarly, this Fisher contraction condition for three maps C8 on a metric space is obtained from this 3.13 when b is equal to 0 and n is equal to 1. So on the other hand, Zervik started the study of Minkowski fixed point theorem for a system of maps. So I think time, so just I will describe in short that we have also the Zervik extend the Zervik result for this is given for the multivalued maps. So recently this Warkowski generalized the Banach contraction principle by introducing new kind of contraction called F contraction and provide some fixed point theorem for self map satisfying the F contraction condition. The following definition is the concept of F contraction which introduced by Warkowski. So this was given, but this definition is given by the Wodgowski, that this F contraction map, and we have taken this extend this F contraction map for product of metric spaces. So here there are some definitions following this. We have also used the Hardy-Rogers type F contraction for the self map. Yesterday, some speaker also discussed about this F contraction. So this is defined for the Hardy-Rogers type F contraction here. So later on, the several authors have extended the generalized results of the Warkowski, improving the condition of F contraction. In this presentation, we combine the idea of Metkwski and the Sigantio-Vetro and proved a fixed point theorem for system of n maps on the finite product of metric spaces. So here it is. This is the result is stated here by taking the contraction F contraction conditions, and then we have the system of maps. This Tix as equal to xi. So these are the examples which illustrate our results. We have a corollary for this. This let xi be the complete metric space and tix to xi I is equal to 1 to n be the maps if there is f belong to f and this tau is greater than 0, then non-negative numbers. This aik defined in the 3.1 and 3.2, 3.4 and the following hold. So then the system of equation, this xi is equal to tix, I will have a unique solution. So here the remark 3.1 of Cesaro-Vetro may be obtained as a special case from this theorem 4.1 when we take yd is equal to xi di and this t is equal to ti, I is equal to 1 to n and n is equal to 1. Taking this again d is equal to this xi di where t is equal to ti and I is equal to 1 to n, beta gamma delta is equal to L is equal to 0 and n is equal to 1 with a11 is equal to 1 in theorem 4.1. We obtained theorem 2.1 of Wardowski 44. Sorry. So now there are some applications of 4.2 to study the existence and uniqueness of the bounded solutions of the system of functional equations when you are taking this phi I t is equal to h I t, phi 1 f1 t1 and phi n is equal to ftn, where this phi 1 are the unknown functions for an arbitrary L y FIR denote the linear space of all functions, and this IVR denote the real subspace of bounded function. So then is a Banach space. So we have taken this result for this one and use this condition for this for the solution. So replacing the set of metric spaces, the LP, and assuming that the functions formed are continuous, one could show the unique bounded solution must be continuous. Under the assumption that L is the real interval, the integrable solutions of the system were considered by J. Metwowski. So the differentiable solution of the system 4.6 were treated by J. Kominek, see also 18. So here we can now what is the further scope of this results that initially once I met Professor Metkwski, so he says that when we are taking here n is some finite number, so what will is it possible to find that when this n is tending to infinity, so how we can what will be the results for this when we are taking the n is equal to infinity. And so this is actually this is the work done from the by myself and the research scholars, so from since 1990 up to this day. So I think it is enough, and so thank you very much.
All right. Thank you so much, Dr. Gairola. It was a nice presentation.